Hello, my name is Gaith Bakar, and basically this is demonstration number 3 for Math 3B. So the first question actually says, explain what an analytic function is. Use the properties of analytic functions to show that f of x is equal to x cubed plus 2x plus 1 times cosine of 15x squared is analytic at x equals 0 and write its Maclaurin series. So basically, an analytic function is a function that can be expressed as a sum of powers. So that's the first thing. Second thing, we need to prove that this function is an analytic function using the properties. So basically, I compose the two functions and I compose the entire function into two different functions, f of x and g of x. So basically, f of x is x cubed plus 2x plus 1. This is a polynomial which is differentiable everywhere. Therefore, it's analytic for all x values, including 0. The second function is actually g of x is equal to cosine of 15x squared. So also the cosine function is differentiable everywhere in x, including x equals 0. Now we need actually to write the Maclaurin series for this function. So basically x cubed plus 2x plus 1 is already expanded. However, the cosine 15x squared, we need to expand it into this form. So right now, after we expanded the cosine 15x squared to this form, we need to multiply it by the x cubed plus 2x plus 1, which at the end gives us this Maclaurin series right here. The second question actually asks us use a power series to determine all general solution to the following ordinary differential equations in an interval containing 0. So basically, this is the function required. So we need to find all general solutions to this following ordinary differential equation. So first of all, y of x is equal to this series. So now we need to differentiate the y of x. So y prime is equal to this series, which we can simplify it into this here, into this series. So right now, after we found y prime, we're gonna substitute y prime into our ordinary differential equation right here. So it's x times this y prime we found. So it's x times this series is equal to y, which is we found it's right here. So after that, actually, we need to divide by x to get rid of all. We need to combine all x's. So we have the series here times xn plus 1 because we have here an x and an x, which is equal to this series times x to the power of n. So now we equate coefficients of like powers of x. So at the end, we get n plus 1 times bn plus 1 is equal to bn plus 1 is equal to bn over n plus 1. So right now we need to find b1, b2, b3, which gives us 1 over 2, 1 over 6. So the solution to the xy is equal xy prime equal y is given by this. So this is actually the general solution for this ordinary differential equation. The third question, which I think is the easiest question, it's actually right. The Taylor series for f of x is equal to the radical of x at x centered at 81. So first of all, we need to show how to find the formula of the general coefficients. So basically, we start by differentiating the function into as much as we can. However, I stopped at the fourth differentiable. So it's root of x, 1 over 2 root of x, 1 over 4, x to the power 3 over 2, 3 over 8, x 5 to the power over 2, and so on. After that, I substituted where it's centered in the function. So actually, it's centered at 81. So I started substituting x for 81, and I got these numbers right here. So that's how we found this formula of general coefficients right here. Second of all, we need to use show that the series converges using the root test on interval 0 and 162. So basically, the root test is actually the limit as n approaches infinity. We open absolute values. We put bn plus 1 over bn, which gives us this limit right here after, inserting n plus 1 into our function. So after some nasty algebra, like it's a really complex algebra, we get this solution right here. And after more simplification, we get 1 over 81 times the limit as n approaches infinity of 2n plus 1, 2n minus 1 over 2n plus 1 times 2n. So this factors all out to 1 over 81. Now, since 1 over 81 is less than 0, this converges absolutely on the interval. So basically, the ratio test, if the L is less than 1, then it converges absolutely. So the third question is that Show that the series converges at the endpoints x equals 0 and x equal 162 by using the appropriate test, alternating series test, or comparison test. So basically, if we did plug, we found here the differential equations. If we plug for x plus x1, x2, x3, x4, we can see here it's an alternating series because there's a change in signs, negative, positive, negative, and so on. So I'm going to use the alternating series test. So basically, when you use the alternating series test, the terms approach zero as n increases. So as x increases, the terms approaches zero. So the series converges on x equals zero. However, for x equal 162, we use the ratio test, which is 9n plus 1 over an, which is 1 over 81. Again, since 1 over 81 is less than 1, the series also converges on x equal 162. Therefore, the entire series converges absolutely on the interval from x from 0 to 162, and it's included. So yeah, because we tested the endpoints. And yeah, that's my demonstration. Thank you.